As part of the Micro and Smart Systems course, we will continue with the modeling. In the last lecture, we had discussed the electrostatic system modeling, where we had discussed how the elastic mechanics and electrostatics couple with each other, leading to interesting phenomenon which is known as pull-in phenomenon. We also talked about the pull-up phenomenon. Now, today we will continue the discussion and introduce what happens when we consider the dynamics of such a coupled system. So, we will continue with the coupled modeling, but move from statics to dynamics. When we do that, we also need to bring in the fluidic effects, which is a very important aspect of microsystems. We are going to cover just a little bit of that microfluidics aspect as it relates to modeling the coupled behavior that exists in electrostatic and elastic systems. Okay, let us just briefly review what we discussed in the last lecture. When we have the potential energy, which we had written it as this potential energy, which is this if I call it P it is half k x square, where x is the displacement of the top plate that is moving in a parallel plate capacitor, minus half c v square, where c is epsilon naught a by g naught minus x times v square. So, that is the electrostatic energy. We discussed why it should be a negative sign, and then we have the strain energy, spring energy half k x square, this is the potential energy. If we plot it for a voltage V1 as it is shown here, we get a curve like this. We have 3 solutions for this one dimensional approximate problem. There are 2 minima and a maximum. All 3 are equilibrium solutions. The minima correspond to the stable equilibrium and maximum corresponds to unstable equilibrium. So, we have a situation like that, and as we increase the voltage, let us say V2, then obviously this equilibrium solution of minimum has to increase, because we get more displacement when we increase the voltage, and the unstable one also moves towards this way, this dashed line here, which is G naught over 3, 1/3 of the gap. That unstable equilibrium solution value decreases, it comes like this. So, at some point, which we call the pull in voltage, the stable and unstable coalesce into one. Beyond that, there is no more stable solution apart from this infeasible one, because this is all after G naught, that is one plate is going through the other plate, that is not a realistic solution. So, after that we do not have any realistic stable solution, which is we call pull in phenomena. So, if you take the 2 plates, when you increase the voltage, it will move a little bit, at some point it will suddenly jump up, jump down and pull in, that is what we call pull in phenomenon. Okay. So, the equations you saw, taking this potential energy, we have to make the second derivative of potential energy equal to 0, because that is what we see here, and then the first derivative being 0, that is this equation comes from dou P e by dou x being equal to 0. When you solve that, you get that instability occurs at 1/3 the gap between the 2 plates. So, the formula for that pull in voltage was derived to be what is shown here. Depends of course on the spring constant k, that is the stiffness of the structure. Remember that this k is simply a lumped parameter indicator of the stiffness of the structure, and G naught is the gap between the 2 electrodes of the parallel plate capacitor, epsilon is the permittivity if it is free medium air, and A is the overlapping area of the plates. So, here if we have the situation like that, when we apply an voltage, that is pull in voltage, it just reaches that 1/3 of the gap and then just pulls in. If anything more than that, just pulls in as it is shown here. And then when you imagine that there is also a dielectric layer in between, even after pull in, short circuit does not occur. So, we do see that in that case the pull-in voltage is given by this formula. Essentially, this is the new part where the thickness of dielectric divided by the relative dielectric coefficient or dielectric constant of that material epsilon r, that is effective thickness that adds to this G naught, otherwise the formula is the same, 8 K effective gap, that is G naught plus T d divided by epsilon r cubed divided by 27 epsilon naught A, whatever we had in the previous one without the dielectric layer, which is this. Okay. Effective layer G becomes G naught plus dielectric thickness divided by dielectric constant. Now, we saw that it also leads to another phenomenon called pull up phenomenon. As you increase the voltage, we go like this, at some point just pulls in, goes to the G naught, that is this plate would reach this point, and then now if we decrease the voltage, it will not jump back up immediately. That is because there is enough electrostatic force to keep it in the down state. So, it will remain like that until the voltage is decreased to something called V pull up, where it just pulls back up again. Here in the curve, x value will decrease. So, the plate has gone down, now it just stays there for some time and then pulls back up and then follows the equation. So, it goes like this, goes here and then comes back. Okay. This is a strange phenomenon, and this has been used in devices, and we had talked about this particular device. Now, let us look at the dynamic behavior. Now, what we consider the static behavior. So, here we have to apply the voltage very slowly to characterize it as a static or quasi static phenomenon, but if your voltage is changed rapidly or applied suddenly, then what happens? It turns out that there is another pull-in voltage that we can define, which is called dynamic pull-in voltage. So, here again we are plotting the potential energy. We are showing a situation where imagine that there is a ball. Okay. If there is a landscape like this, when I leave it there, it will come here and then it will go to the same height. Okay. For any reason, let us say for voltage larger than what whose energy is shown here, then if this were to be higher than this unstable point, note that this stable point here, unstable point start moving towards each other. So, if I were to leave a ball here, you can imagine that it comes down and then it can go up to that level. So, it will obviously go over this hill and still has some potential energy left, which converts to kinetic energy, just go down the hill and again pull in occurs. So, here even before the minimum and maximum coalesce into one stable equilibrium, equilibrium solution, not stable, that will be kind of a transition. After that it will not exist at all. In other words, in your cubic equation, two roots will become complex conjugate, while the third root remains real, which is this, which is not of interest to us. Okay. So, now we need to work out another formula for pull-in voltage, where the potential energy is initial one when x equal to 0 is equal to the potential energy at the unstable equilibrium. That is one equation. Other is of course that this has to satisfy the equilibrium equation, meaning dPe by dx is equal to 0 there. If you do that, then for a voltage that is more than dynamic pull-in voltage, but less than the static pull-in voltage, pull-in will still occur. That is one effect in the dynamic behavior. You can work out the dynamic pull-in voltage by solving these two equations. One is dPe by dx is equal to 0, other is Pe, let us say you get some x here, Pe evaluated at x, okay, x equal to x is equal to Pe at x equal to 0. That is, we are saying potential energy here is same as here, that is x equal to 0, that is the starting point, and x equal to where dP by dx equal to 0, slope is equal to 0. These two equations you solve, then you get both the value of x at which dynamic pulling occurs as well as the voltage at which it occurs, just as we had gotten that in the previous case, where let us just take a quick look at that. We had one equation here, another equation here, we were able to solve for x and then for v. Similarly, we have two equations and two unknowns and we can solve for it. Okay. Now, if it is like this, like a ramp and go, there will be a transient and there will be accompanying effect for it. But imagine that this voltage here is actually a sinusoidal input, okay, something like that. This voltage goes from, there is a bias and then it just goes like this. There is a DC component which is this much, over that we have the AC component that goes up and down. Now, then what happens? So, we have to go to our 1D model. So far we had Kx equal to the force, this is the mechanical force, this is electrostatic force. We equated those two and had gotten the equation. Now, we have to add another term which is mx double dot. This is the what we call inertia term. Inertia term. If we add that, then we have to solve this ordinary differential equation in x, second derivative in time. So, it is second order system. Any dynamic system is a second order system when we consider in this particle form or rigid body form or other ways. Okay. Now, when we solve it, we get something, but you know that in this case, as you might recall the lecture that we had on the vibrations in general, a concept called resonance should come to your mind. Resonance occurs when the frequency of the forcing function, in this case the voltage, coincides with the frequency of the natural frequency of the system. When both are the same, things will be in phase in a way that it will start exerting more and more displacement. Actually, the force will be the same, just that the consequence, the amplitude of the system keeps on growing and we get a lot of displacement, and that is what you would expect to happen. But in this particular problem, this parallel plate, as you increase the voltage of your frequency of your voltage, resonance occurs much sooner. The reason for that we can understand by looking at, let us erase these lines. Okay. If you look at that, there is in the force term there is a V square. When you have VDC and VAC, so VDC plus VAC sin omega t square, when you have that we get VDC square 2 VDC VAC sin omega t and VAC square sin square omega t, right. Because of sin square, essentially there is a 2 omega term, because you know how to write cosine 2 omega as sin square omega, right. So, whenever you have sin square omega, it means that there is a 2 omega harmonic term. So, when this 2 omega is equal to natural frequency, again we should expect to have resonance occurring, and that is why when this 2 omega is equal to omega n, which is the natural frequency, as we call natural frequency, that is when the applied omega is only half of natural frequency, already we will have resonance occurring in this system. That is one thing that we need to remember, because there is a V square non-linear term for the force. Now, here is another equation that we should pay attention to, because we had discussed, apart from lumped modeling, what if we take a distributed model such as a beam model. So, here earlier we did not have this term, this is a new term which is the inertia term. Okay. Inertia term is simply mx double dot. In the case of a beam, if u is the transverse deflection, which is a function of x, the axial distance, that is u of x. So, rho w t will be mass per unit length, and then u double dot will be like x double dot equivalent du d square u by dt square, and then this other portion is the same thing. This is the beam equation, this is electrostatic force, okay, and that is the equation that we need to solve, and it will display the same behavior as this 1D model that we have shown. So, that will have a static Poisson voltage, dynamic Poisson voltage, and all other features. Okay. Now, when we talk about damping, we have to deal with the fluids, because microsystems necessarily involve fluids unless it is vacuum packaged. If I take an accelerometer and vacuum package it, there is no really fluidic effect there, because only the solid moves, but even under packaging there is nothing like a perfect vacuum packaging, there is nothing like a perfect vacuum. So, you do have some air and you have to consider the effect of that, and that happens in many modes in microsystems. We will only consider a few standard modes, and before that let us discuss the basic fluid mechanics that will enable us to think about problems where we can estimate. So, the damping term here, this is the inertia term, let us write things down that we know already, and this is stiffness term, and this is our damping term. That is in the 1D model, mx double dot plus bx dot plus kx equal to forcing term, that in this case is electrostatic. In the case of beam modeling, we have the same thing, inertia term, damping term, stiffness term, and the forcing term. That can be on the right hand side or minus on the left hand side. So, we get the dynamic equation. So, we have discussed how to get K, we have discussed how to get M also, because when you want to get equivalent inertia, we use the fact that kinetic energy of the deforming system should be same as the lumped model's kinetic energy, just like the strain energy of the lumped spring is same as the strain energy of the elastic body. So, similarly, what concept gives us the ability to compute this B? That is our main point of discussion. So, we are not going to discuss fluid mechanics at length, and in fact, that is not possible in a lecture on microsystems. So, you have to refer to books or take a course or watch a course that discusses fluid mechanics in general. Today, we will discuss fluid mechanics as it pertains to microsystems very briefly. Okay. So, we will have a slight review, I would not even say review, it is just a few comments on fluid mechanics in general, and try to derive the expressions for getting damping coefficient that you can put in our lumped modeling or 3-dimensional modeling or 2-dimensional distributed modeling. Let us say fluid mechanics are microfluidics, as it is called, microfluidics. It is basically the study of fluids at the micro scale. So, you might ask, what is different about fluid mechanics at micro scale as opposed to fluid mechanics at the macro scale? We did not bring it up when we were discussing the modeling of solids. Whatever beam theory that applies to macro scale structures, we said that the same thing applies to micro scale structures as well. So, how are fluids different? Fluids are different from solids in one fundamental way, which is that they cannot take any shear force. That is one thing, they are very different from solids, we know, but technically put, that is the effect. Other is they have viscosity. Viscosity is the difference that you will find between water and let us say honey. So, you can see that something like honey is very sticky. If you put a pen or your finger into honey, try to move it versus try to do the same thing in water, you will find that moving your finger in water is very easy, whereas in honey you find lot of resistance for your motion. That is the viscous effect. That is a property of fluids, that is very important. Okay. Now, if you look at fluids in general, since they cannot take shear stress, or in other words their shape changes when you apply some shear drastically, okay, that causes a lot of differences in the way solids and fluids behave. And when you come to micro scale, the properties of fluid will change much more quickly than properties of solids change. Properties of solids also change when you go to micro scale, but you have to go to very much smaller scale as opposed to what happens at the fluids. Main thing is what we call continuum assumption. Continuum assumption. In order to do the modeling with the differential equations and other things that we have discussed, we have to worry about this continuum assumption, meaning how continuously the species, there can be particles or atoms or molecules, how closely are they located to each other. That is, if I take a chunk of material, take a little piece out of it, I cut a little piece out of it, out of that little piece I take another little piece and I keep on doing it many times. When I do that, can I end up with some species, okay, how many ever times I do it? If that is true, we call that material a continuum. So, everything is continuous to each other. Okay. So, that depends on the volume of object we take, but when it comes to micro scale, okay, solid continuum assumption holds good much longer, that is much longer when I say you can go to much smaller scales than fluid mechanics. Okay. There are lot of reasons for it, we will just look at couple of reasons today. And to write the governing equations for solid mechanics, so let us just review that. Solid mechanics, we needed two things. One is equilibrium, okay, equilibrium, and that is usually force equilibrium that we wanted, and other is the stress strain relationship. Stress strain relationship, which is known as Hooke's law. Okay. That is all we need to formulate the equations for solid mechanics, and there are a lot of details of course, but everything follows from force equilibrium and stress strain relationship, also known as constitutive relationship. When it comes to fluid mechanics, it is much more complicated, but we can say that these two derives from two things. One is continuity and the other is linear momentum conservation. So, if there is a fluid something, okay. Now, if I take a small control volume, how much enters, how much leaves, if there is really no source within it, it has to be 0, whatever enters, whatever goes out, the net flow will be 0. You need to have that continuity, but also linear momentum, because all around fluid particles are going to experience forces. So, if you take that linear momentum corresponding to that, that conservation of that, these two will lead to what are called Navier-Stokes equations. We certainly are not going to derive them or even state them, we will just look at couple of flow patterns that we find in microsystems. Okay. Let us take the first example of what happens in the case of comb drives. Let us say that this portion is fixed comb drives, and then in between we have moving comb finger. So, that means that this is going to go back and forth. So, we had earlier assumed that we have a parallel plate capacitor. Now, there were the comb fingers. If you imagine, actually I will put my fingers to show. If you have fingers like this, they will go in and out like this, okay, or they have actually a surface. So, it will go like this. If I look at these two, now one I can say it is fixed, other is moving like that. So, in between there is fluid, all right. So, if we have one plate at the bottom and another plate at the top, let us assume that this part is fixed and there is fluid in it, showing like a dots, but there is a continuum fluid here. And now, if this were to be moving with some velocity v 0, top plate is moving with velocity v 0, what will happen? So, for that let us imagine that there is a water tank and you put a very thin glass plate that you are holding with our hand and you put it over it and try to move. Okay. You try to move, you will feel that there is some resistance to your motion, as opposed to putting it on a solid and try to move. Then also there will be resistance, either the plate will simply move over the solid or the friction is high enough, you might move the solid also along with your plate. Okay. When it comes to fluid, the fluid that is over here on this edge will not move because it is in touch with something that is fixed, whereas things that is over this edge has to move with the same velocity v 0. So, we can show velocity profile here, that is v 0, okay. This is 0. It turns out that if you apply the Navier-Stokes equation here with assumptions of what happens in a one dimensional flow such as this, you can derive that the second derivative is 0 or the second derivative of the velocity is 0 or the first derivative is linearly varying, and that is what we are showing here. So, velocity will be 0 here and v 0 here, that is same as the top plate, in between it will linearly vary like this. So, we can write that as this velocity of the fluid anywhere. Let us take this gap as h, okay. Velocity profile that we have written, this v can be written as y divided by h into v naught. So, what is y here? We say this is y axis, this is x axis. Okay. When y is equal to 0, v is obviously equal to 0. When y equal to h, that is at the top place, it has a velocity of v 0 because h and h will cancel and become 1. So, we get v equal to v 0. So, this is the velocity. So, in this flow where we have one plate fixed like this, like what happens in comb fingers, in a comb drive and other structures that are there in accelerometers, many of them. If you take an accelerometer, there is a proof mass and the proof mass is going to move for the in plane acceleration and it experiences a fluid force because there is air underneath, air on the top, it is moving and we have to consider that force. The reason we need to look at fluid mechanics is that the damping is a result of the fluid force and there is dissipation. So, we talked about viscosity, that is moving your finger in thick honey, then you are actually dissipating some of the force, and as opposed to moving in water which is not that viscous, but there also there is some dissipation. To capture the dissipation, we need to look at fluid mechanics. The spring is only going to store energy and that energy is strain energy, and a mass inertia effects is also another kind of energy which is a kinetic energy, whereas the damping term leads to energy that is lost, and that is what we are after to get that damping coefficient B. So, we have this plate fixed and the top one is moving, we said is moving with velocity v 0, and we wrote that velocity profile, that is V0 there and then moving, in other words V anywhere here, okay, is equal to V0 into y by h, okay, that is in this direction. Now, we have to consider the force, or we call it shear, because if this plate is there in a water tank, if you try to move the plate, it will not be there, there will be some force that it feels. Now, we define this shear stress, which is the force experienced per unit area of the plate that you are moving over water or any other liquid. Here at micro scale, even in the presence of air, when the things move, it experiences substantial shear due to the fluid beneath. That shear stress is given by this relationship. Okay. This is like a constitutive law, just like Hooke's law we had, which relates stress and strain. Here it relates the stress and something like a strain like quantity, that is how velocity varies in the y direction, dou v by dou y. So, in this case dou v by dou y is minus eta v naught by h. Look at that, v is this. So, dou v by dou y is simply equal to v naught by h. Okay. Now, when we want to get the force at the wall, let us say over here, okay, that is actually the damping force that acts on the top plate as you move. That is the resistance that you feel. If you have, again you have to try this experiment on a tank of water, take a plank, a plastic plate or something, or even a steel plate, steel dish, and you put that there, try to move slowly versus try to move fast. When you try to move fast, there will be more force as opposed to doing slowly. So, let us say that we have a flat surface of water in a tank, you put our hand, or even with the hand also you can try. When you move slowly, it will be less force. If you try to move fast, it will try to drag more, that is called drag. The same thing ships will experience when they are going in water or boats or anything else. So, that is apparent here in our relationship when you say the shear stress is proportional to the velocity. So, shear force is a damping force, we have to multiply tau by area of cross section. So, when we do that, I substitute for this tau, which is minus eta into area of cross section h times v naught. Okay. We have not defined what this eta is. That is a term that we have used already, and that is called the viscosity. There is a kinematic and dynamic viscosity, two phrases, but we are not going to get into the details of that, because at micro scale one needs to actually modify the viscosity based on an assumption called slip flow velocity. Here we have seen that at the wall the velocity is 0, but that is not necessarily the case in the case of microfluidic channels and flows through microfluidic channel. There will be a slip between the wall and the fluid particles that are there. So, this viscosity can be modified to account for those effects, and when you go down to really small scales, then you have to treat each fluid particle as a separate entity and do molecular dynamic simulation, where you would just write Newton's laws for every particle and integrate and take the interactions among all these particles and do what is called molecular dynamic simulation or MDS. Okay. But for now, let us say this particular flow where we have damping force tau A equal to this. Now, if you see, this is force, okay. Let us call this Fd, damping force, is equal to something times velocity. So, this is velocity. If you recall the expression that we had written for one dimensional model were m times x double dot, second derivative of the displacement, which is acceleration, accelerant times mass is inertia force, plus we had b x dot, that is some b times velocity of the thing, plus k times displacement, which is a spring force, equal to the forcing function. Okay. This is the forcing function, the force that we have applied externally on the thing, and this is spring force. Once again, to recall, this is inertia force. Okay. Now, what is this? This is a damping force. So, damping force is, or at least viscous damping force such as the one that we are considering now, is proportional to the velocity, and the constant proportionality is our B. So, if you look at this, this is what is B, and the sign tells you that when you are moving in one direction, the damping force will be there, because the drag, that is why it is called drag, it drags you back. If you move in this direction, there will be a drag an airplane or a boat that goes in the other direction. So, essentially we can say from here the B is equal to viscosity times area of cross section divided by the gap between the plates, and that is how we need to take the B. So, if we have a comb drive, okay, let us say that I will show a number of combs now, number of comb fingers, not really combs. We need to erase this because we need to have room for other comb fingers to come in. So, this is let us say this is the fixed comb, and there will be a moving comb. Okay. Let us say this is our proof mass, and let us say this is the axis of symmetry. So, the similar thing is there mirrored this side. Now, this will have some suspension for it to move. Suspension may be a beam like this, okay, which will, and also another beam may be here, which will make it move back and forth this way. We can get K from these things, okay, and of course, mass is there, that itself gives the mass. For mx double dot we have that, K times x we have, but the damping comes over here. So, this is the fixed plate and this is the moving plate with some velocity. For that we have derived B equal to eta times area by the gap. So, the gap here now will be h, and there will be area, that will be length of the comb times the thickness of the comb. Okay. L is length of the comb finger and T is thickness, out of plane thickness of the comb finger. If you do that, you get the B, and that is what you would use to do the dynamics. That is one effect that we consider. This kind of flow that we just discussed, that is one plate stationary, other plate moving, such as this, there is a name for it, and that is Couette flow. Couette flow. Under Couette flow, which happens in accelerometers and comb drives and many other devices, we can put an equivalent damping like a lumped constant, that is eta viscosity times area of cross section divided by the gap between the fixed surface and the moving surface. Okay. Now, there are lot more things that we need to consider in when it comes to fluid mechanics, but we will consider another flow. We consider what is called a Couette flow. Let us consider another flow which is called Poisson flow. Or pipe flow. So, here imagine that we have a pipe in microfluidics, no fluid will be going through it and coming out. Okay. Inside what happens? And let us say there is a pressure drop across this. There is a delta P, actually this is delta L, and pressure drop across delta L is let us say delta p. This is actually L, let us call it y delta L, just call it L. Pressure drop across that, let us say delta p. Then what happens from velocity from here to here? So, there also the walls of this tube that we are looking at, they will experience, this is a cylindrical surface if you take, they will experience some shear stress as well. How does that that causes dissipation, also causes a shear force on the body? How do you estimate that? If you consider the Poisson flow condition, which you say if I take a section, the velocity profile is parabolic. Again, if you consider, if you look up any fluid mechanics book, they tell you how the conditions of Poisson flow reduce the velocity profile to parabolic, which is given by this velocity v. It will be 1 over 2 eta times y, again this is our y axis, okay, h minus y, where h is the hydraulic diameter of this flow. Circular pipe, it is just h. For other cross section, the equivalent hydraulic diameter, h minus y times the pressure drop, okay, that k is written as minus delta p by L. This is a pressure drop. So, that is how you put in this equation, you get this. Now, if you take this velocity and then write the shear stress like we did, that is viscosity eta times dou u or dou v, the velocity, by dou x, that is this is our x direction, okay. Viscosity times the velocity gradient in the x direction will give you the shear stress that is acting, and if you multiply that by the area that you take here, you get the shear force. If you work it all out, you would get the B here. So, we are skipping the derivation, so that you can work it out for this case following what we did earlier, that is previous example of Couette flow. If you do the same thing for Poisson flow, then we would get this B to be 12 eta L divided by W h cube, where W is the wall thickness into the paper, okay. So, in the pipe flow like this, if you take that, that is your damping coefficient, and that you can take into a formula in the lumped modeling and do the dynamics, okay. If you want to do the full analysis, like we do 3-dimensional analysis for an elastic solid body, here you have to use fluid dynamics equations, where we have to solve the so called Navier-Stokes equations and get the result. There are a lot of finite fluid simulation software programs out there, any one of them can do it, or it is always better to take a sample problem, small problem, and try to code it ourselves. So, we discussed two flows now, Couette flow and Poisson flow. For Couette flow, we derived the damping coefficient to be eta times A by the h, the gap between the fixed plate and the moving plate, and Poisson flow, which goes in a pipe where the things are going, in terms of the pressure drop that occurs there, we derived a equivalent damping coefficient, which is this. Now, let us switch to another very interesting effect of the fluids that happens. First, we said if the plate is moving like it happens in accelerometer proof mass moving over the air film, then you have the Couette flow condition. But there is another case where the accelerometer, Z-axis accelerometer, which can move up and down like this. There is a bottom substrate, other one goes up and down, then the air here gets squeezed as the plate is moving. It is squeezed and it can move out from the sides, because you have the finite size of a plate. When it moves like this, all the air that is here, that can escape from the sides, but there will be different effects based on whether I am doing it slowly or fast. Imagine a cycle pump. When you try to push the pump slowly, you would not feel as much resistance from the fluid as you would feel if you were trying to pump fast. The faster you do it, the more resistance due to viscosity that you feel in a cycle pump. Similarly, here when this top plate or a beam over here, okay, let us get the pen here, this top plate here, where it moves slowly, you would receive much less damping force or fluid force as opposed to doing it very fast. We will analyze that. So, what we want essentially is to obtain this B that occurs in this B u dot term. This is the inertia term I, this is the damping term, that is what we will discuss now. This is a stiffness term, this is a forcing function for electrostatics which is there. So, now we are looking at a problem that operates in 3 domains. There is elastic solid domain and there is electrostatic energy domain, which is the forcing function here, and then we have the fluid that we are considering now here, that effect of damping due to that. So, it is a coupled field problem of 3 things. So, in order to analyze this, we have to discuss this squeezed film effect, which is modeled using a special form of the fluid governing equation, that is Navier-Stokes equation, called a Reynolds equation. So, this is a Reynolds equation. In fact, that is a lot of adjectives. It is isothermal, the temperature is not changing, isothermal, compressible because you are squeezing the air, it is a compressible, narrow gap. So, you assume that along this y direction, okay, your pressure is not changing, pressure is changing only here, but not in this direction over here. Okay. And the film of air is very thin, that is narrow gap I already said, and this particular equation actually comes from lubrication theory. So, if you imagine journal bearing where there is a fixed shaft and actually not even fixed, they relatively rotate the journal and the shaft there, in between there is a narrow gap, and that narrow gap, if you put oil, the oil is getting squeezed, and that is where this Reynolds equation is very useful and very well developed. There are a lot of solutions worked out, and now we are using that to model the damping due to the squeeze film effect, and something else that happens besides damping is the squeeze film effect. Okay. Now, what is that Reynolds equation? So, here is the equation, looks a bit intimidating at first sight, but we will simplify it so that we can extract the B from it. So, here we have the pressure, okay, we have the plate, there is x and y. So, we assume that there is pressure in the z direction is not changing, only the x and y direction is changing. So, we have put P x y, and the gap is also x y, that is the gap between the 2 plates. When the beam just moves like this, the gap x y will be the same everywhere. When the beam deforms like this, then there will be gap different. That is dou P g divided by dou t. So, it is a time varying, it is a dynamics equation. We have this nu for viscosity, earlier we had used eta. So, whatever we had eta earlier is same as this nu here, and then del dot, that is divergence, that is x y z components. Here you have to take dou of the x component by dou x plus dou of the y component over dou z, dou of z component by dou z, that is what the divergence means. And then P g cube, notice that there is cube just like we had cubed in the electrostatics in the pull-in formula, and then we had the gradient of the pressure, that is del P is dou P by dou x in the ith direction, it is a vector gradient, z direction, that is x direction, y direction, dou P by dou z, k, that is what this means. In x y, this our final z term will not be there. So, that is the equation. It can be solved numerically, okay, but we will try to simplify it for one dimensional modeling, where we will say that it is a rigid plate that is moving. Like parallel plate approximation, we had a spring to account for the stiffness, so the plate is like a rigid mass moving up and down. If rigid plate, then this g will not depend on x and y anymore, we just have one gap for the entire plate, that is one simplification. And this dou by dou x, dou by dou y we do here, that will not affect this g, because g does not depend on x and y. So, you can take it out, that is shown here, and you can further write this p times del p with little bit of vector manipulation, del square p square x y, okay. And then you make one more assumption, that the p varies only in this direction, but not in the x direction, because if it is very long plate, which is what we will have either in a comb finger, we can say that nothing is changing so much in the x direction, all the change in the y direction where the squeezing is going to occur. So, if you consider that, then P depends only on the y direction, P y g dou by dou t of that, g cube by 12 eta, and we have this equation. This is still non-linear because there is p square, del square, g cube, and all of these things, and p and gap both are occurring as a product form. There is a lot of non-linearity. So, you can linearize around a point p0 and g0 and substitute the linearized part. So, you will get an equation in del p and del g, small pressure perturbation, small gap perturbation. That is, you imagine the plate to be slightly vibrating like this. That is, you have a small voltage, alternating voltage component. So, because that plate is vibrating like this, one is fixed, other is vibrating like that. So, if you take this equation, introduce some non-dimensional variables such as these for pressure, position, pressure and gap. Okay. Position is y by w, width of the plate, this is pressure, atmospheric pressure outside, and the original gap g naught. Then you get an equation. Then you can solve by using separation of variables. There is something that depends only on the position, something depends on the time, because pressure is going to depend on position and time. We can separate it out, which is standard technique for solving differential equations. Then this one can be solved this way by using an impulse excitation on the problem and try to get the solution. Again, you should work out the details of this, because deriving this takes a long time, but we have just shown the steps. You look at the steps carefully, and it is actually worked out in a couple of books. So, the solution of this is given like this. That solution is shown here for that equation that we showed in the last slide. Then we have some unknown constants, you can determine them from the boundary conditions. Okay. Then you will get a series solution such as this, only odd n, because even n will get cancelled out. There is something called sigma n, which is also used in these equations, which is shown as n pi, which occurs in this series solution as well. Now, we can get a force term from this, because this is a pressure multiplied by area, I will get the force. That is what we are doing here, integration. So, you get the force term, you take Laplace transform of this, and you will see why we take that. So, it comes something like this. Now, if you say n to the 4 and n is odd, that is 1, 3, 9, 1, 3, 5, 7, 9. If you stop at only n equal to 1, that is just an approximation to first order, you get a transfer function that looks like this. Okay. Actually, we have to include this S also. Okay. Which circuit in terms of resistor and capacitor that we imagine, which have this transfer function, and that turns out to be a resistor which is like a damper, and a capacitor which is like a spring. Mechanically, this is like a spring and this is like a damper. This is the B, this is K. That means that the squeeze film effect has two things, one is damping, other is the air acts like air spring. So, both effects come up, and they depending on the frequency of how fast your plate is moving. If it is moving slowly, you will see more of the air, the viscous effect. If you do it fast, then you actually see the air spring. So, it is not complete dissipation effect or viscous effect that you feel when you do it very fast, you actually see the air spring. So, effectively, in addition to mechanical spring, now we will have the squeeze film spring and the damper. Okay, and this is the effect. So, we have to consider the air spring effect also, that is a function of the frequency, and the K is given by this in terms of P naught and G naught, and B is given by these quantities. So, this is what we need to do to solve a problem with a lumped model. Okay. But if you want to do it, you can take this equation, solve this using the isothermal equation and our mechanical equation. There is inertia term, there is stiffness term, there is a forcing term, then this is the fluid force, the pressure times the area per unit length. If you do this, you have to put across the length of the plate and solve these two coupled equations. Already we have mechanical electrostatic coupled here, we need to couple with the fluidic equation also. When you solve it, for different, actually for interesting, to make it interesting, finite difference method for solving the pressure equation, that is that equation, finite element for solving the mechanics equation, and electrostatics is just parallel plate approximation. Right now you can get a solution where you can get the pressure field without linearization. This is a full nonlinear equation can be solved. This is a bit advanced, so it is a long expression. From there if we expand, we can solve it numerically, which is what we can do when things are not amenable for simple analytical solutions. You can get this the plate displacement as a function of time, which is quite complicated. Okay, all that can be done. To summarize, let us take a problem such as this, where there is a diaphragm that moves up and down, there are two valves that move in and out like this, there is electrostatic force. So, there is elastic domain, there is a fluidic domain, and electrostatic force. There very strange things can happen, and all that can be modeled using basic equation that we have discussed. What we have not done in detail is the fluidic effects. So, you have to read about Navier-Stokes equations and their special conditions as to when they can be simplified to Queued flow or Poisson flow or squeeze film isothermal Reynolds flow, and then use the appropriate simplification to solve the problems, or go to the differential equation and solve the complete numerical solution. Let us just note down our main points, that microsystems involve tightly integrated multiple energetic phenomenon, and that leads to differential equations that are coupled to each other, and all of these have to solve together. But what we can benefit from is reduced order lumped models, or what are called macro model. They capture the macro effect of the things, and in a simple form, that M for inertia, K for stiffness, and B for damping. That also we discussed for couple of cases. In the next lecture, we will talk about electrothermal actuators. There again multiple fields coupled to each other. Thank you.